Okay, so when we finished off, we had just finished our question about our coffee maker. Oh, let's get back up to that. We found our p-value was rather high. Or I'm sorry, our p-value was very low, so we did in fact reject the null hypothesis. We rejected it. We found there was strong evidence the mean amount of coffee dispensed by the machine was less than 10 fluid ounces. And that would tell us that we go into doing a conference interval in order to find out what do we think the mean average amount of coffee being distributed is. And just a quick reminder, confidence intervals always follow the same format. It's going to be the estimate plus or minus the margin of error. Now in this case, we're going to start off with our mean estimate is from our sample plus or minus our t-score times our standard error for the mean. In this case, we're going to go to our t-distribution table. So we find 95% confidence. We look all the way down here at the bottom. 95%, that means we have 5% left inside of our two tails. We had 19 degrees of freedom. So our critical value for t is 2.093. We plug this into our formula along with our 9.845. Our standard error is our sample standard deviation divided by square root of sample size. And so we find our intervals 9.75 to 9.94 fluid ounces. Now interpreting this, of course, we want to use full sentences and using the context of the problem. Or we are 95% confident the machine dispenses an average of 9.75 and 9.94 fluid ounces of coffee per cup. Now that's just one example. We can also do a second one here. A company has set a goal of developing a battery that lasts over 5 hours or 300 minutes in continuous use. In a first test of 12 of these batteries, the following lifespans were measured in minutes. Now we want to use this data, we're going to collect it, load it inside of our T1, we have all of our raw data now. Is this evidence the company has met its goal? Or in other words, we want to know if the mean battery lifespan exceeds the 300-minute goal set by the manufacturer. We have 12 battery lifespans in our sample to test the claim. So this is what we want to test. This is what we're looking for in our final solution. First thing is, can we even run the test? Well, often that means we need to check our assumptions, and so far we said that means we need randomization. We don't actually have a random set of batteries, but this is a first test of 12 of these batteries. It's a new type of battery. Well, I'm sorry, I got ahead of myself. So first thing is we have to define our parameter, and we've talked about this so much, it's the lifespan of the battery. Or really, mu is the true average in minutes lifespan of the battery. So my hypothesis, my null hypothesis is that no, we haven't made it yet. That would just be that my mean time is 300 minutes. Our goal is to prove that we've exceeded that. So our alternative hypothesis is that mu is now above 300 minutes. The batteries have a mean lifespan is greater than 300. That would tell us that the goal has been met. In order to track this, though, we need our randomization condition. As I said, these were not a random sample. I got ahead of myself. I skipped hypothesis, went right to check our condition and model. But they're probably representative. So I don't have randomization, but they are representative. Second thing, I need my distribution to be at least approximately normal. Now, if I pull up a histogram, I pulled it up, it looks like this. Now, depending on your class widths, they could look a little different. But there's only 12 batteries to work from. That's not a very large sample size. But if I plot my normal probability, it looks like this, which this is pretty linear. This suggests to me I do have nearly normal data. So I think I've met it. It was roughly unimodal, it was roughly symmetric, but really it was a normal probability plot. That's what really sold me that I probably have a normal model can describe these batteries. So what I'm going to do, since the conditions have been met, we can do a one sample t-test for the mean with 11 degrees of freedom, one less than our sample size. So my mechanics, my sample size we said was 12 degrees of freedom, we said we're 11, and then I had to take the mean of all those batteries at 306.25. And of course, I also need my sample standard deviation because I don't know what the population is, so we're going to use my sample, 29.31 minutes. Now, if I take all this, I need to convert to find my t-score. So t for 11, so I can draw this my curve, mark in my time that I'm looking for, but now I need my t-value. So 306.25 minus 300 divided by the standard error of the means, or 29.31 divided by square root of 12. If I calculate all this, I find it's 0.7387. So my t-score, I filled it in down here on the bottom, 0.7387. And now I'm looking for a p-value. The probability, my mean, my x-bar, would exceed 306.25. And that's going to be the same as saying the probability that my t for 11 degrees of freedom, would exceed 0.7387. I put this in calculator, I go TCDF, my lower limit is 0.7387, my upper limit I can put 99, degrees of freedom I load 11, and I find it's 0.238. Well, that's a fairly large p-value. In fact, it's very large. Because of that, I fail to reject the null hypothesis. There's no evidence the mean battery lifespan has exceeded 300 minutes. It doesn't appear the company has met its goal. Now, what I can do, though, is give them a better idea about where they're actually at. They may not have exceeded their goal, but where are they probably landing? So I can give them a 90% confidence interval for the battery time. In order to do this, my conditions had been met, so I'm just going to create a one sample t interval of 90% confidence. So I'm going to take my mean, add or subtract my margin of error, and I'm going to find, and we calculate the same way as before. I 90% confidence, that's 10% left inside the two tails. I look it up on my table for 11 degrees of freedom, I got 1.796. Multiply it by my standard error of the means, or interval, 291.05 to 321.45. So I have to interpret this though. I am 90% confident the mean battery lifespan is between 291.05 and 321.45 minutes. And that's it. I've done it. But let's say they've come to me and said they want another trial. But this time, they need to know how many batteries do we need to test so we can be 95% sure of estimating the mean lifespan to within 15 minutes. And then they say to within 5. Well, let me take them back and start with just the 15 minutes. Before we go into this, let's talk about what we're dealing with here. So we have a little bit of an issue. We're dealing with a t distribution and the t tables. And one of the things about those is that every different degree of freedom, we have different t values. So we have a problem here. What do I do when changing my sample size is going to change my t values, but I need that in order to find this? For example, in order to solve this, we know we're normally going to do a sample size in order to solve for n. Well, normally we've just taken our margin of error, which in this case, the margin of error for mean times, well, that's t asterisk times the standard error of the mean, or just t asterisk, critical value, times the standard deviation divided, I'm sorry, that should have been the sample standard deviation, sample standard deviation divided by the square root of the sample size. So that's a problem. I don't know what I'm going to do for my t, my critical value, because every different sample size could potentially give me a different t. And actually, let's be better about this. In this case, we wanted a 95% sure. We wanted 95% confidence. So our two-tail probability, we are in this column, so it wasn't the correct column. But if it's a sample size of 1, well, my t-value is 12.7. But sample size of 5, it's 2 point. Or I'm sorry, sample size of 2. Sample size of 6. Because my degrees of freedom, if I had 10 degrees of freedom, or sample size of 11, my t-value is now 2.2. Sample size of 14, I get a different t-value. I get different critical values. So I can't use this formula to solve for it. Not initially. Because every single different sample size gives me a different t. So instead, we're going to make our first estimate based off a z critical value. Our standard that we used before was our z critical values for this. So we'll use this for our initial estimate. So in this case, we're on 95% confidence. Then that means I have 5% inside of the two tails. If I take that 5%, and I cut it in half, I have 0.025. So I go second vars, inverse norm, area is 0.025 with mean and standard deviation of 1. And I find out that that gives me a negative 1.95 or 1.96. So I use that for my initial value. Now the next question is, We said our margin of error is within 15 minutes, so I do know this side will be 15 minutes. And then my standard deviation, well, we're going to use what we had before. We had 29.31. Now in order to find this, I'm going to do a little bit of algebra, move a few things around. So I have the square root of n, make that a little bit cleaner. The square root of n is going to be equal to 1.96 divided by 15 times 29.31. I can solve for this side and then square each so that n is going to be, it looks like it's going to be approximately 14.67. So that gives me an approximation of my n. So for my first initial assumption, I'd say I have 15. Should be my sample size. But what I'm going to do now is this used a z-score. Now that I have an initial figure, I'll use that to calculate for t. So my margin of error is still going to be 15 minutes. But this time we're going to solve for our t asterisk, but with 14 degrees of freedom. So I can pull up that table we just had a moment ago. So if I have 14 degrees of freedom, don't need any of these arrows now. If I have 14 degrees of freedom, let's get our highlighter out. I want 14 degrees of freedom. I'm in the two tails have 5%. So I'm in this column. And I'm assuming for the intersection is 2.145. So my t critical value is going to be 2.145. And this time I'm still solving for n, but now I have a better t value to use for this. So if I do this, we solve this, we have the square root of n. So let's go ahead and do a little bit of manipulation here. Square root of n is going to be equal to 2.145 divided by 15 times 29.31. And now if we use this information, let's see. Oh, that's what went wrong. Sorry about that. I was doing something on our screen. We solve for this. We're going to get n. Let's see what happened here. A little slight issue. Hang on. Now solving for this, we get n is 17.56. Or n, I need 18 in my sample. So when we're going to need to find for these sample sizes, what we have to do is start with a z critical value in order to get an initial estimate for a t critical value. And using that, we solve for our sample size required. And that's what I did on this other slide. I just thought it would work a little bit better if we saw how that worked, how that went together. So for those of you who are in class, we did this a little bit differently. We still found our t critical values. We calculated we'd need about 18 batteries to get within 15 minutes with 95% confidence. Now at this point, the question then said, how about within 5 minutes? Now we can redo this process. We can always redo this process. We can also reflect on the fact that that's 1/3 of our original value, of our 15-minute time. In order to do that, we know it's going to take more batteries. We said before, if you just double your sample size, that won't even cut it in half. In fact, we solved for this before by finding if my margin of error was equal to a critical value, which that won't change, my standard error, my standard deviation from the sample size, divided by square root of sample size. But I want to cut it in 1/3. So that means 1/3 of my margin of error has to equal, well, I still need that z critical value. It's still going to be my standard deviation of the sample size. And now it's going to be the square root of n. But for me to get that 1/3 in here, well, I could have it out here, but I really want to get it in there next to that n somehow. In order to do that, I have to square it. Sorry about that extra line that showed up. Okay, but it's going to put 9 on the inside. I would need 9 times as many. So now I wouldn't need 18 batteries. I need 162. Okay, so what we can remember is that to cut an error in half, you have to multiply sample size by 4. Now you've seen here to do it into a third, multiply by 9. If I want to cut it into a quarter, I'll multiply by 16, so on and so forth. That's a rule of, it's not a rule of thumb, it's mathematically true. If you remember that, it might save you a little bit of time if you get a question like that on a test. So moving on, we have some facts about the t-distribution. Fact number 1, the density curve of the t-distribution is similar to the normal curve. Specifically, it's bell-shaped and symmetrical about 0. Secondly, the spread of the t-distribution, it's a little bit greater than the normal distribution. There's more in the tails because we're using samples. We're using the standard deviation of samples for our standard deviation of population. So we have more variation. There's more variability. Our tails need to be a little bit thicker. Next thing, as the degrees of freedom increase, the curve approaches normal curve. Now technically, it actually becomes normal curve as n goes to the limit of infinity. But you don't need to worry about that in this class. The main thing is our standard deviation from a sample, it estimates the standard deviation of the population more accurately the larger n becomes. When you think about this, this makes sense. If I have a standard deviation for, say, the entire school, I have 1,600 students, I have a standard deviation based on a sample of 50. Well, if I sampled all 1,600 students, I'm going to have the population standard deviation. The closer I get to that 1,600, the more my sample standard deviation, or my sample error, is going to approach the true standard deviation. So also some rules for how we can use the t-test. Now, ideally, the population has a normal distribution. There's some things we've said have a normal distribution. If we want to talk about the height of men, that's generally normally distributed. The height of women, normally distributed. SAT scores, ACT scores, IQ test scores, these things are generally normally distributed. But a lot of the things in the world are not normally distributed. They're not truly normally distributed. So here's what we can do. If I have sample sizes less than 15, I can use the procedures that are for data that's close to normal. But I can't use these procedures if the data is clearly non-normal or if outliers are present. Now, if my data is nearly normal, but it has outliers, and my sample size is less than 15, I need to do my calculations both with the outliers and without the outliers and see if it changes my answers. Okay? That's also why we don't really like the small sample sizes. That can happen. Second rule, if I have sample sizes between 15 to 40, I can use the t-procedures as long as the data is unimodal and it's reasonably symmetric. It's kind of linear on the normal probability plot. It doesn't have to be as pretty anymore. It can be a little bit uglier. Okay. Now the best thing, the gold standard we get to have is when we have more than 40, we can do these t-procedures pretty much no matter how the data looks at this point. It doesn't matter how skewed it is. I've sampled enough people. And this refers back to that central limit theorem and how it creates the data to look more normal. Okay, so once we have samples of more than 40, we get to use these procedures all the time. Now, using the TI-84s or the 83s, we can create 95% confidence intervals. And we're going to use that for this problem. So I have a simple random sample of 75 male adults who live in a particular suburb. They took part in a study, checked the amount of time they spent per week doing rigorous exercise. It indicated a mean of 73 minutes with a standard deviation of 21 minutes. So first thing is, what I'm interested in finding is the true mean rigorous exercise time for all males in the suburb. That's what I would look for. I'm going to find a confidence interval that I'm hoping will capture that. I'm going to do it to a 95% confidence interval. So I need to know some information. Let's just assume for the moment that all my assumptions are met. First thing is my mean time. Well, it told me it was 73 minutes. I had to have my sample standard deviation. Well, it told me it was 21 minutes. My confidence, we said, was 0.95. Degrees of freedom is 1 less than my sample size. So 75 minus 1, I get 74. So now I can find my t critical value. So we use inverse t. We found is 1.99. Using this information, I can find a regular confidence interval. The other thing I can do is use a calculator. So I'm going to go stat. I'm going to go test. I'm going to choose the t interval. So I want a t-based interval. On that screen, it gives me a couple options. I can use data or I can use statistics. Statistics, a numerical summary of a sample. I have that information. I don't have all the raw data, so I can't have loaded it in L1 and tell the calculator where it's stored. So I go to stats and I load my X bar. What was the mean amount of time? 73 minutes. Sample standard deviation, 21 minutes. My N, I had 75. I tell my confidence level is 95. And it tells me my interval then is 68.168 to 77.832. So I can interpret this. I'm 95% confident the interval is, like I said, and we can do it manually. Doesn't change anything. We still got 68.17, 77.83. Well, that's what we had here too. So I have my data either way. We're 95% confident that male adults living in this suburb exercise between 68 and 77.83 minutes. You can also test in the calculator. Now, I say on here, go ahead and try it because you could have had the coffee data from previous questions would still be loaded. And in that case, I'll pull up the test. Yeah, we'll keep the writing. Okay. So we have our calculator again. Now I may have to type some of this data in and that'll be okay. I'll bring my calculator, bring it over. Okay, I'm gonna have to type some of it in again. So if I turn on the calculator, let's get that out the way. I'm gonna go to my stat test. I have a bunch of tests here. I want the t test, because it offers me 2 sample z tests and 2 sample t tests, but I just had a single sample. So I'm gonna go to just the t test. And t-test asks me for data or stats. Well, we still have some more statistical data. Let's see if I still have my summaries here. I don't have my summaries written down. On my coffee data, that was that first question we did from the part 1 of the video. We had some stats from that. We said their mean amount of coffee, well, we were testing, was it 10 ounces? Our mean amount of coffee, we said in our sample was 9.845. And our sample standard deviation was 0.199. Our sample size were 20 cups of coffee. We were testing was the mu, and these are the options we have, not equal to the null, less than the null, or greater than the null. And we said we want to find out, were they shortchanging? Was it less than the null? Okay, that's what we're looking to find evidence for. So let me tell you to calculate. We calculate it, it finds me my t-scores, it tells me what my critical value is, but it gives me my p-value of 0.0012. That's a very low p. I would reject my null hypothesis. In fact, that's the same score we found doing it manually. The other thing we can do with that screen is stat test. We'll go back to t-test. And this time we'll tell it to draw the picture for us. And what it'll do is it'll draw the t-curve for us. It will mark approximately where our t-score was, and it's shaded in. Now, we were so far up on the t-score, on the negative, we're so far down there, it's not really showing as a shaded area because we're over 3 standard deviations away. It's just not on the screen. It was that rare for it to happen. That's what got such a low p-value. Now we take our stat, test, and let's go to our t-interval. We saw before, it would often bring over the copy. It would bring over the data. We notice it did the same thing here. Now the last time we ran I want to make sure, 95% margin of error. So we'll still leave it at 95%. Or I'm sorry, 95% confidence level. So I'm going to leave it at 95%, and we'll run it. And it says it's between 9.75 to 9.94 fluid ounces is 95% confidence. It's still the same information, hasn't changed. We can use a calculator to find the same values. So having done that, what we want to do now, let's try that again. Okay. So we find our values before. Sorry, it goes backwards a little bit. Okay. So we can run the test in calculator. We tried it. We saw the same results. And we're going to have to play around the calculator a bit. The way we're going to do that, we had some assignment questions. So I want to finish up the assignment questions. We're probably looking at the next time we meet, do a brief review, then do a quiz on this type of material. All right, so I look forward to seeing you soon. Have a good day.